Yes, okay, let's start a bit with a question. Who of you already knows about Coreboot? Okay, so for the stream that's about 80% of the room. And who runs Coreboot already on the machine? Okay, that's about 30% of the room. Okay, so why is that? Well, first of all, Coreboot, as you might know, just runs on old ThinkPads. Who runs it on their gaming rig, their new Intel laptop, whatever? Well, we're here to change that view on the topic. And we're here to give you a bit more trust in the firmware that runs your everyday activities. First of all, for the people that don't know Coreboot, Coreboot is the host firmware of your laptop, tower PC, any machine really, that runs all your activities, anything, your server, that runs your Minecraft server, that runs your FTP server with all your legally acquired movies. Yeah, and in the slang we call it the BIOS. The Coreboot project was started by Ron Minish as Linux BIOS back in 1999, and we renamed it later to Coreboot to sound more broad, more unique, and not as confusing in January of 2008. Yeah. If you want a bit more background on all of that, we can recommend the talks on 33C3 and 34C3. Bootstrapping is likely more secure laptop and bringing Linux back to server boot ROMs with nerve and heads. So, what are the benefits of running Coreboot? Well, first of all, as you might have, everyone here in the room who works for a big IT company might have seen what proprietary code looks like. And anyone who is just a bit active in open source also knows how open source code looks like. And it's not a big secret that the Linux kernel, an open source kernel, is more stable and more popular in enterprise. Well, that's just the advantage of open source. And Coreboot itself only focuses on the hardware initialization part of the BIOS or the firmware, so it doesn't deal with any file system drivers or networking drivers, and that just makes it way less complex than any dollar vendor firmware you could get on the market. And this also limits the attack vector, then unlike most popular UEFI implementations, what we use, for example, EDK2, you just have a less complex code base, and less complexity in this case also means less percentage that you have any vulnerability. Also, as you might see in a second, it's insanely fast when booting. Also, why is it used already? Yeah, Cisco is using Coreboot, for example, for their networking gear. Yes, it's enterprise gear, it has multiple stages of booting, and it is slow when booting, but this is one of the examples of enterprises that already use Coreboot to secure their boot vector a bit and like reduce any attack vectors you have. Any hardware you get by Google, like Chromebooks, Chromeboxes, Chromecasts, routers, whatever, also most certainly all run Coreboot. See Ellie's talk on last year's Congress on that. Yeah, and industrial machinery, obviously, data centers, look at the Open Compute project, consumer hardware, System76 already ships with Coreboot, Star Labs, Purism, Nova, custom PC engines, for example. So like if you have a router from PC engines or used one of the devices as a router, you run Coreboot already. Yeah, now back to our mantra from before. Why is it so hard to run Coreboot? Well, Intel, our friends, already came apart from us and said, oh yeah, BIOS, firmware, that's an attack vector. Anybody could just flash any firmware on there, and you don't even need to infect your PC with a virus if you can just go around the kernel and already put an attack vector in the firmware. And AMD did the same with their platform Secure Boot. And in a nutshell, that prevents any firmware that's not signed by our lovely overlords, the manufacturers, to get loaded onto our hardware. Qualcomm, Samsung, Google also have the same thing on their ARM64 devices. So like, good luck porting Coreboot to your phone. Yeah, Intel implemented that in the management engine, and that's what we're going to look at today. And that just starts before the x86 cores even boot or even start. So it checks the firmware that would get loaded into the CPU before it gets loaded into. And that's checked against a private key in an eFuse. Yeah, that's all done in factory. So if you got a device with an eFuse blown and a private key installed, it's basically impossible for us to load Coreboot into it. But that assumes that the manufacturer even remember to do so. Because what happens if you just get a device in manufacturing mode with no eFuse blown, no private key installed, and you're just being able to bypass all around it. So what we're going to look at today is, I got a device that, the eFuse isn't blown, so I can load Coreboot onto it, but where do I start? But don't worry, we got you covered. Ellie's going to tell you all about porting Coreboot to a new device in the next section. But first of all, let's explain how x68, 64 systems boot.
Hi. So first, we should explain the small microcontroller you have on your mainboard, usually located between the PCI Express slots. It's usually called SuperIO or embedded controller. Embedded controllers are mostly common on laptops, but they are mostly the same, just a little bit different, as we explain later. Then you have a platform controller hub, which can be either a dedicated chipset. Oh, okay. I think my microphone just died.
Yeah, okay.
Okay.
Yeah.
Yeah. So. I mean,
Welcome to the Chaos Communication Congress, where chaos is pre-programmed.
Oh. Okay. It wouldn't be a congress without technical issues. Oh.
Yeah. I mean, we are the last talk, so no worries, we got time.
Thank you. Okay, thank you. Yeah, so where we are? Yeah, so it can be either like a dedicated chipset on the main board, or it can be integrated in the SoC itself. That's called platform controller hub or chipset. Then you have main CPU, or also it can be integrated together on laptops. Of course, you have your RAM slots, or it can be solder RAM. And so we mostly will focus on desktop system because they're a bit easier to get working than laptops. So as we explain, I will show you a slide in a second how different power rails work on the main board. So basically, when you press the power on the main board, what happens? So first, when you press the power button, the SuperIO or embedded controller comes out of reset, and tells platform controller hub, or basically supplies the voltages to platform controller hub, which starts loading code from SPI chip. And then CPU takes over, configures the cache as RAM to load the first stage. So, like this is the main board that's in the system. You can see that you plug the power into 24-pin ATX power connector. It has always on power rail 5-volt standby that is supplying power to SuperIO. And SuperIO is listening basically for power button press to supply all the voltages. When you press the power button, it basically shorts pins. Like usually you have like green and black wire in the ATX24 connector. So when you short those rails, the power supply starts supplying power. We probably all know how that works, so that's taken care of by the SuperIO or embedded controller, and then the code execution starts. So, yeah. So the first stage that is being loaded, that's exclusive to, let's say, AMD CPUs, even though it's Intel talk. I know people will be curious. So AMD CPUs have platform security processor, which is like a tiny ARM core, and the CPU itself basically has the same functionality as management engine. The difference is that while Intel CPUs have their own like blob that is configuring the memory controller, the AMD CPUs have like memory controller functionality in the PSP. So first the memory controller in the PSP starts and configures the RAM, and then x86 cores come out of reset. That's why it's called VerState before boot block, because that is not being executed on x86 cores, that's on ARM. But we focus on Intel today because AMD still has some work to do. But yeah. So in the boot block, Intel CPUs configure CPU cache as memory to execute code before memory controller is up. You can also configure GPIOs for UART, so you can get output in boot block, like what is happening. Then it's loading FSPM, which FSP stands for Firmware Support Package. That's like a blob you get from Intel. It's very bespoke, but it's basically so that they can avoid handing the code to us. They provide you with the API that you can configure from Coreboot or other solution. And you can configure different parameters, like if you want to enable XMP, if you want to configure memory in a specific way, and if it trains the memory successfully, the DRAM training data is saved in like a region that's called MRC cache, memory controller cache. So when you power on the system next time, it does not have to train memory again. So then, once that finishes, the RAM stage gets loaded. That's the next stage in Coreboot. That's loading FSPS, FSP Silicon. And that's configuring like interrupt controllers, secondary CPU cores, PCI Express logic, all other GPIOs. It writes API tables so that OS can know how to talk to the hardware you have, especially when you have a laptop. And then when that everything is fine, everything finishes, then it drops to payload. We will tell you what are the options for payloads. Like we said, Coreboot is only taking care of like platform initialization, so you have another set of software you can choose that will interface with your like file system to load the kernel and such. Okay, 1 second, please. So. Okay, so SuperIOs are like very simple microcontrollers. They usually don't have their own SPI storage, so you have to configure registers from the host firmware. And legacy designs, like for instance, if you had like system, let's say in 2002, it will have like floppy controller, IDE, parallel port, like LPT. On those like newer systems, it's not really used. Like sometimes they use older designs, but these LDNs are disabled. Like some manufacturers do not populate the serial ports, but all SuperIOs provide you with RS-232, which you can get really easy serial output from. You have environment controller, so SuperIO can listen to like CPU temperature, and based on the temperature reading it's receiving, it can control fans via PWM. Like you have, for instance, like PWM fan headers on the mainboard, so that functionality is also controlled by SuperIO or embedded controller. PSU controller, that's common between like laptops, and it's basically like in the past we had like 2 ports, now it was 1 port, now they got rid of it on some main boards. I don't know why, they shouldn't, but then GPIO, which is usually under LDN 7, if I remember correctly. It's basically telling SuperIO to, for instance, hold the 3 volt standby to keep RAM powered, or other functionality. You really need datasheet to understand what it means. Like, we will show later how that looks. Something that I haven't seen on like any mainboards yet is consumer IR. Like, you can have like infrared, like a remote that will be also controlled by SuperIO. So these days there are like 2 manufacturers. One is Nuvoton. They're really nice. They have most datasheets either listed on their website, or they're very nice. You can just send them an email and they hand you the datasheet. That's very nice. ITE, which is pain and suffering. Like, even if you have NDA, if you're a board vendor that is working with them, you either don't get a response, or it's a very plain response, and you can basically forget about getting datasheet unless you like find it on like Baidu or something like that. Like, it's really crazy. So, yeah. So this is an example of configuration for SuperIO. You can see that under PNP 2E 1.1, so that's LDN1, we configure COM port, which is RS-232. LDN4 is an environment controller. Of course, I had to truncate the output a little bit, but you get the idea. You can configure the sensors, how they're connected, like which fans output are present on the board, with comment like which fan is it. You can see that I left LDN 5 and 6 disabled because this mainboard does not have PS2 functionality, and like basic GPIO, and again LDN like A is consumer IR, which I left disabled. Hopefully that's understandable. In case of embedded controllers, they mostly have the same functionality, but they run their own firmware. Like you should focus on the main chip with sticker AMI FTO. I don't know why they put the sticker on it. It has nothing to do with the firmware. And the small SPI chip, I believe it was like 1 megabit. Yes, 1 megabit, which runs its own firmware on like most designs, like from Lenovo or ITE, use either compact, like really bespoke closed source firmware to basically configure the registers, or you can have like Chrome OS embedded controller, which is written in C. It's based on Zephyr OS these days. It's open source. It's very nice to work with, and you can modify it. So you have like basically 2 options. It's either open source or not. So the difference is that you don't have to configure registers from host firmware. The configuration is stored in SPIs. So maybe it may be a bit easier for beginners, but then again, if you have a laptop, when you dump ACPI from the stock firmware, you will have to write ACPI tables to have like battery monitoring and stuff. So it can be a bit tricky. So the fun part, like not many people know about, is that the keyboard on the laptops is still basically connected over PS2. So embedded controllers on the laptop scan the keyboard matrix and then forward the events to the operating system under PS2. Sometimes you can have special functionality like controlling the light on the keyboard, but that's embedded controller. And it can also control stuff like USB-C power delivery, monitor battery status. If you like close the lid, it should suspend the machine, and stuff like that. Okay. Do you want to talk about this one?
Yeah, okay, I can do that. So how do we verify that Coreboot is disabled or not? First of all, we use a tool called RDMSR, and for that we need a kernel module, which it interfaces with. So just check with modprobe that MSR is enabled. After that, as a super user, you can execute rdmsr and 0x13a. And if you get a status of 0, so 0x7 and a few zeros, it means it's unprovisioned, aka the e-fuse isn't blown. So if you have a status like that, you know, oh hey, I can flash any firmware I want on this device. So yeah. Another way is you can to check is Intel ME tool. So for example, if you're planning to buy a board, you can just get it from the newest firmware from their website and check with Intel ME tool or similar, or the Intel Flash Image tool, where if that flag is set or if it's not set. But yeah, we can't tell you where you find that because that's an illegal instruction. So yeah.
All right, thanks. So it's on some Skylake, Kaby Lake, and some Coffee Lake systems. There was a vulnerability in management engine versions that made Kukri, the author of BootGuard utility, managed to exploit by downgrading management engine to vulnerable version. Basically, they managed to gain code execution and bypass the BootGuard check that checks the status of e-fuses in Platform Controller Hub. If you're interested in details, I encourage you to just have a look at the links because we don't really have much time to get into details. But yeah, on like ThinkPad T480 or other like Optiplex 3050, like basically most Skylake, Kaby Lake, and some Coffee Lake systems that 6, 7, 8 generation, it's now possible to port Coreboot to it. So thank you, mate, or mate. Okay, so getting down from the stock firmware. So first we need to boot Linux. Of course, Windows will not work for this. Sorry about that. We boot with the highest log level, we disable SL Linux if you use Fedora, and IO memory relax so that you can access more stuff without like kernel protection. We need to install tools like LSPCI, LSUSB, ACPI tool, ACPI dump. You can basically read the list on the screen. And basically we grab all the logs. Again, LSPCI, which will give you a list of all PCI Express devices in the system, as well as registers used with the do specific command, which can be helpful for debugging like bar space and other like weird issues you might run into. LSUSB, self-explanatory. SuperIO tool will provide you if it's supported, if your SuperIO is supported by SuperIO tool. It will basically give you a list of registers and brackets that you should configure. In your firmware. It's basically in the brackets, it will tell you which registers in your firmware are configured differently than they are by default according to the datasheet. Intel tool will tell you the status of a lot of stuff, but we're most interested in GPIO configuration that we dumped. Later we can parse it with Intel P2M, which we get into. EC tool, it's basically the same as SuperIO tool. MSR tool, I don't even remember if it's really necessary these days, but DMID code, which will give you SM bias information. It can be helpful to like see like memory sticks, how they're configured, and you might also want to clone some kind of configuration for network adapters. NVRAM tool, again, I never really needed it, but sometimes it can be useful to read the NVRAM configuration. DMSC is self-explanatory. ACPI dump will give you, like, instead of just copying the files from the kernel, it will give you a list, like, let's say, like a hex dump of the ACPI that you can later do an ACPI extract and decompile it with an ISL tool. and that gives you basically a full list of XPI tables provided by the stock firmware. And that's very helpful, especially if you have a laptop with embedded controller that you will have to basically match the CPI tables for embedded controller. Like R230 can be helpful to have like dump the registers for stuff like trackpad, audio amplifiers, and other R230 devices that you might have in the system. The next one is grabbing the Intel VBIOS. They call it video BIOS tables. It's basically VBIOS on the Intel GPUs, which is stored in the stock firmware. You can basically grab it from Linux and place it in your Coreboot tree. That works. Precedent routes can be helpful if you are working with less supported SoC. You may run into issues where it might drop off the bus, like PCI Express devices might drop off the bus or anything like that. I doubt that it will happen with most CPUs in the tree, but it might happen, so better safe than sorry. FlashProc will, if the chip configuration is not locked down and your flash chip and piece cage is supported in FlashProc, sorry, it will help you get your stock firmware, which is especially helpful if your manufacturer does not provide downloads. Tuxedo. Then we dump basically pin configuration from ALSA, which basically tells us how different pins are, which pins are enabled from HD audio perspective, and we can use this information to build a table that I will also show you later. Right. And if you need help figuring out how to, because on Intel GPUs you have different video outputs that are enabled in VBT or VBIOS. If you dump a dmask with VBT, it will basically bring you, oh hey, VBT tells us that this output is enabled, this one is disabled, so that's how you can get this information. Okay, so that's the basically the tree for Coreboot's mainboard. Like you get source mainboard of manufacturer and model name, and you can basically read it on the screen. We don't really have much time, sorry, to get into that, but basically this is like different files and where they are being executed or provide the information, like which flash chip it has, and so on. Okay, so you have all those dumps. So what now? So basically, you should find the mainboard with the similar SoC in your in the Coreboot tree. Start modifying it or write it from scratch. You can look at your SoC's chipset.cb for device tree syntax if you're missing devices. For FSP options, there are FSP headers that you can find in this path. If you can, find the SuperIO datasheet. Like, you might have some luck, you might not. Good luck. And basically, for download datasheets for your platform controller hub, and beware that Intel likes to hide GPIO table inside the PDF. So, then you should configure UART. You will really need some kind of output to get logs. You can have RS-232, UART straight out of SoC, SOSI cable on Chrome OS devices, SMBus console, which I personally haven't used, or you can write the logs to SPI chip and then read it from with the programmer. So this is basically how you would configure SuperIO RS-232, like on this specific mainboard, but you get the idea. This is how you would configure UART straight from the SoC of course, you probably will likely need schematics or find it with a logic analyzer. Yeah. So then let's see a GPIO, device tree, how to configure the RAM slots, PCI Express, USB, and HD audio. So first, we dumped the GPIO configuration using Intel tool. Then we parsed it with a tool called Intel P2M, which gives us a very nice table that we can just use in Coreboot as a pretty much ready table. You probably will need to dump it multiple times because if you plug the monitor into DisplayPort, it might change the GPIO configuration. It may be changed by SCPI if you have audio amplifiers. So basically you will have to dump them multiple times, compare them, and refer to the table that Intel hides in the PDF. And important is that please do not reconfigure GPIO. If it's set as output, please do not configure it as input and vice versa, because you can basically blow up stuff on your mainboard. So, yeah. So, memory slots, that is pretty easy. Just a piece of code. You see that you have two memory channels. So under SPD 50, 51, you have primary channel, first and second slot. Secondary channel, you have first and second slot. So the first slots are always 52, second is 51 to 53. And then you basically configure stuff you need for your memory, like SPD profile for XMP and stuff. Of course, you will need to test this, but that's how you configure memory slots. Hopefully that works. Yeah, that's for a GPU. You get the information from about DDI links from the DMESC that I showed you earlier. Yeah. Then PCI Express, it's sometimes FSP is remapping the slots, so hopefully you should populate all of them. If it's not possible, you might change them, plug in the card, see if it's working. Thankfully, on most platforms, Linux kernel will just tell you, oh, that's root port 6, that's root port 9. So hopefully that will work. So that's a bit fiddly. Hopefully you have schematics. If not, well, that's of course a bit harder. But yeah, I mean, it's not that complicated. So for instance, you see PCI 060 is PEG 0 according to chipset.cb. So you enable device reference PEG 0 on, and that's your PCI Express 4.0 root port is connected directly to the CPU. And that's another example. The first one is the PCI Express 4.0 connected to the CPU, and second is connected to the platform controller hub at 3.0. Right. USB. Sometimes you can get this mapping from LS USB, but without schematics, it's a bit complicated. So you will need to basically, what I would suggest, if you don't have schematic, just enable them all and start disabling stuff. If it breaks, revert. That's probably the quickest way to do it. Like HD audio, you might recognize those pin assignments from the demos we made earlier. So basically, vendor ID 8086, which is Intel, 281C, which is Alder Lake, then it's HDMI, number of entries. So that's basically all the information you can get from DMESC and ALSA dumps. That's not really very complicated. Right,
yeah.
That's yours.
Yeah, now for the payload. This is the next thing we have in the boot cycle after Coreboot, which is basically where as Coreboot developers, our governance of the firmware ends. But this is also not to be forgotten, because when you want to Coreboot your PC, you need a payload. And it's basically picking a poison. We have EDK2, which is a slimmed-down version of a full UEFI service. We have CBIOS, which is for legacy BIOS booting. U-boot, which is a much simpler UEFI implementation than EDK2. Grub is basically a universal booter. It just looks ugly. And it works with Linux. It won't work with Windows, obviously. And it's kind of untested with BSD. By the way, if you want to use Windows or OS X or something, just use EDK2 and just install it using UEFI. Then there's also Linux boot, which should be a topic for a whole talk itself. It is basically a Linux kernel that uses the kexec function in the kernel to just boot different kernel. So you have a Linux kernel, for example, in your BIOS, your firmware, and that boots your Linux kernel on your hard drive.
So you like Linux so much that you boot Linux to boot Linux?
Exactly. Yes, now if we would want to build it, we obviously follow Coreboot's documentation, we build a toolchain, etc. Then you decide if you want to use your manufacturer's IFD and ME regions. Then you make nconfig, configure Coreboot how you like, choose the payload you like, whatever, but ensure to have debug options enabled, because without those you are not able to properly debug all your issues. So like enable serial port, enable all the debugging options for the serial port, yeet all your kernels away, all your cores away to make Coreboot, and have fun. How do we flash it? We use an SPI flasher, something like FT232H, and Raspberry or Glassware interface exporter are worth the price for that. Flashproc is what we recommend for that, and attempt booting. For debugging, that it's a bit different depending on what you corebooted. If you corebooted an SoC, for example, you should look at the schematics of the SoC to find the UART pins that you need to solder to. And yes, have fun soldering now. Otherwise, you can also just use a no modem terminator, for example, for a desktop PC, which we will show in a second. And then you can just connect that to possible RS-232 ports you may have on your main board. Yeah, now you have Coreboot on your laptop, on your computer, whatever, have fun. By the way, when you watch this talk live, we just released Coreboot 24.12. And a little disclaimer, doing it on your primary work machine that you have is probably a bad idea, and don't do it on company hardware. Yeah, but wait, what about AMD? A little discourse on the side. It's technically possible to make Ryzen 5000 laptops supported on memory work, thanks to Chromebooks and whatever Google did. Ryzen 7000s will get a proof of concept of an open silicon support, but that will not work for power management yet. And open silicon and core booting with open silicon support by AMD should be production ready in 2026. So maybe see us again on 41C3. And yeah, now it's time for demo. We have brought a desktop with us, which we will show a Coreboot and what you can do with a desktop PC and a plugged-in GPU that's Corebooted. And in the meantime, my lovely partner Ellie will answer all your questions you have.
Wow, thank you. That was an awesome lot of information. And yeah, we have limited time for questions, but I think we can fit some in. If you do have questions, we have microphones across the room. Please line up. It's also possible to ask questions from the internet using hashtag 38C3zigzag on Mastodon or on Hackint via IRC in the channel 38C3-hall-zigzag. Please, microphone number 1.
Hello, guys. Thank you. An excellent talk. I have a question regarding the flashing, because you mentioned that you just flash the SPI with your build image. Have you any experience using SPI emulators instead of flashing every time?
Yes, of course. We use them at work. They are quite expensive. Like E100 costs 800 euros. And it is using Xilinx Spartan 6 FPGA. So maybe someone could come up with cheaper one, but they are very convenient and very fast. There is a Linux utility called EM100. Yeah, I mean, you just have to specify which chip you want to emulate, like preferably the same one that your mainboard came with. And you can basically feed the mainboard from the flash emulator. And that saves you a lot of time because of having to wait at least 30 seconds for reflash. You just send SPI image to the flash emulator, which takes like 2 seconds, and you can boot. So that is highly recommended, but I wish there was a cheaper solution.
Thank you. Do we have a question from the internet?
Yes. Do you know a general bootloader that is vendor independent and works with all major components?
I'm not sure about this question. Like bootloader. Like that's an important distinction that we have Coreboot, which is doing platform initialization. Then we get a payload, which is like EDK2 U-boot, and then you get a bootloader. So like that's your grab or system deboot. So I'm not sure if I understand the question correctly, but what happens after the payload is up to you.
Okay, I think we can take one more question from microphone 4, please.
Do you have any idea how likely it is that the fuse is not blown and has been forgotten?
Right. So I can tell you that here in Germany, there is a company called Medion, and they very often forgot to blow their own e-fuses. For instance, they forgot to blow e-fuses on their Qualcomm X Elite laptops. I have few mainboards from that company manufactured by vendors like ECS or MSI that don't have blown e-fuses, and I successfully managed to just edit the IFD configuration and just boot modified firmware with whatever I wanted. But you have to check basically.
Okay, thank you.
You're welcome.
Okay, I'm afraid we are running out of time. I think we do have some time to admire that awesome demo that is running by now.
That's Intel Arc GPU running on Coreboot, by the way. As far as I know, it's the first one in the world. So yeah, I mean, it was a bit of a challenge to get it working with resizable bar support, but it's running pretty well, considered it's the first generation Arc GPU. So yeah.
Awesome, thank you.
Yes, so for all the people that say you can't game on Coreboot, we proved you wrong.
I mean, you can also run like Blender and stuff. So it's a 8-core machine, 16 gigs of RAM, DDR4. So you can do whatever you want.
Yeah, have fun.
Okay, so let's hope all of you can attend the next year's Congress with already core-booted machines. Please give our two speakers, Ellie and April, a huge round of applause.